So, Ambisonics. How many of you have heard about Ambisonics before? Yeah, most of you. Okay. How many feel that you know what Ambisonics is? Oh, okay. uh, Not quite as many hands, but okay. We'll take it easy. Some people get confused about Ambisonics. They feel it's a little bit complicated. I don't think there's any reason for that. Well, there is a reason for it, but it doesn't have to be like that. I think the reason why people are a little bit confused sometimes is because ambisonics, like many things, can have several different representations. Some representations can be complicated and some can be easy. And this is nothing in itself complicated. I mean, if you draw a circle in a drawing program, you know that the circle has some sort of representation internally in the program. You don't normally care if the program represents the circle as a center point and a radius, or a center point and a diameter. Maybe it's the corner points of the inscribing square or something. You don't care. You care about the circle and what you can use it for. And this is how, as a user of ambisonics, you should think about ambisonics. You shouldn't care too much about how the signal is represented internally, but you should know at least one representation of what it is, so you know exactly what you can expect to get from ambisonics. So I should maybe broadly say that ambisonics is a way to store and transmit a spatial sound field. And I'll describe very precisely what I mean by that. So I've been working with ambisonics since 2009, like you said, and I've been making software to process ambisonic recordings, and the project I've been working on for the last few years is this microphone here, which can record ambisonic in ambisonic format. So my mind is mostly with microphones now, so I'm going to, after I've explained what ambisonics is, I'm going to explain how to design an ambisonic microphone and some of the challenges involved in doing that. So let me see here. Yeah. Okay. So I will present three different representations of ambisonics tonight. To understand what ambisonics is, it's enough to get one of them. So and I'll do the easiest first while you have the most energy. So if your ambition is just to understand what ambisonics is, you can get ready for about 10 minutes of learning, and then you can relax. If you already know what ambisonics is, I'll go a little bit further. So I hope to bring everyone one step up. It'll be a little bit for everyone, but I'm not sure if I can bring everyone all the way, but there will be something for everyone. Okay, so the most straightforward representation of what ambisonics is the following. Ambisonics is a way to encode all the sound that passes through a point in space, and to divide it into different channels depending on where the sound is coming from. So you divide the space into sectors, and if the sound is coming from, say, this sector, then you route it to channel number 1. If the sound is coming from this sector, you route it to channel number 2 is coming. Okay, so you divide space into a bunch of, well, here the sectors are drawn as little nodules or lobes. So every one of those is supposed to represent one channel, and the direction that it points in indicates which direction it is most sensitive to sound from. So if a sound is moving, if a sound source is moving over the horizon, it will gradually transition from one channel to the next, like the way you would pan a signal from left to right on a mixing disc. And that's pretty much it. I mean, this is not terribly complicated. If you understand this, you understand what ambisonics is. There are a couple of small details that I could add. One important thing is that all of these channels are perfectly in phase. This means you can add them together to create new beams that have different shapes. Let's say you want to cover a whole area over here, which has like a strange square shape or triangle shape. You just add beams until you have the shape that you want. And the second thing, which is important and not quite so intuitive, is if you want a beam which points in a direction other than one of the beams that you already have, you want to have something which is halfway between two of these, there's always a way to combine the beams that you have into a new beam such that the new beam is as sharp as the existing ones. So if you just add two beams, you get one which is wider than what you already have. But you want to keep the sharpness, and there is a way to do it. I suppose many of you are familiar with digital signal processing and resampling. So it's exactly the same process as when you resample an audio signal. If you have sampled the signal at time t equals 0, 1, 2, 3, there is a way to interpolate between your samples to get the values that you're supposed to have at t equals 0.5, 1.5, 2.5, without losing any information. Well, except for round-off errors, but you can have arbitrarily small loss of information when you do that transformation, and it's the same thing here. And the way you do it is actually very similar. You probably already know what kind of interpolation function you should use if you want to interpolate a sampled signal. Can anyone tell me? Sinc function, yes. And if you have a periodic signal, well, then you want a cyclical sinc function. And when we are dealing with a sphere, we're obviously dealing with a cyclical situation. When if you walk around the sphere, you end up where you were. So we need a cyclical sinc function. And this will be our beam shape. To draw the beam shape, we just do the absolute value, create a polar plot out of it, and rotate it around its own axis. So this is the beam shape. If we look at the sinc function, there's a little detail I want to point out. This particular sinc function has 5 peaks, 1, 2, 3, 4, 5. That makes it a 5th order beamformer. You can have more peaks, then you have a higher order than 5th order. So count the number of peaks, and you have the order of your beamformer. More peaks means it also gets narrower, which is the point of having higher order. Another numerical magic number is here. If you count those nodules, there are 36 of them. 36. It doesn't have to be 36. You can have 25 or 16 or 9 or 49. It's always a square number, and the number is related to the ambisonic order that I just mentioned. Those have to fit together. So if you have a 5th order ambisonics like we have here, and the number of nodules will be the ambisonic order plus 1 squared. So 5 plus 1 is 6, squared 36. Okay. And that's pretty much it. Now, this is not the representation that people normally use, and I'm not going to hide it from you. I'm going to tell you which representation is standardized and used for exchanging these recordings. It's a little bit harder to grasp. That's, I think, why people are confused. But like I said, if your goal is just to understand what ambisonics is, you have understood it by now. And this can be used for lots of stuff. I mean, if you have a signal divided into sectors like this, you can send each sector through a different filter, a head-related transfer function, and add them together. Then you have a binaural recording. You can add them together according to the locations of your speakers in a surround speaker system, and you have a surround signal. Or you can do this in 3D, so you have a Dolby Atmos signal. You can, you can extract individual sounds based on their location relative to the microphone. You can change the mic setup. If you make a music recording like this and you're not happy with the way it sounds, you wish you would use a different mic, you can change the mic, because you can emulate all sorts of different mics with this as a starting point. And also, this is not intuitive, but I will try to explain why. Even though all of these beams are in phase, you're not limited to coincident microphone setups when you emulate different microphones based on a signal like this. You can deduce what the sound field is a little bit away from that center point based on all of this spatial information. So you have a very flexible starting point when you have a recording like this. And like I said, it's standardized. So once you made a recording like this, you can ship it off to someone who's going to use the recording. He doesn't need to know what kind of microphone you used, and you don't need to know what kind of application they have in mind for the recording. So it's microphone agnostic and it's loudspeaker agnostic, and it's very, very practical that way. Also, it's free from patents and other trademarks, and well, there are some trademarks, but no, there's nothing which prevents you from using this for free and on the application that you like. So there's a lot of good things to be said about it. Okay, now we get to and this has a name, by the way, or it's very similar to a proposal of a format which has a name, which is called SPS, that's spatial PCM sampling, which was proposed by the late Angelo Farina. It hasn't taken off that format, but I think for didactic purposes, at least it serves a purpose. So this can be converted one-to-one into the standard representation for ambisonics, and that's what I'm gonna bring up now. So for those of you who deal with DSP, you know that a time domain signal can be sent through a Fourier transform, where a sound is converted into a sum of sinuses and cosines. The relationship between this SPS format and ambisonics is exactly the same. It's basically a spherical Fourier transform. So you take the it's the same thing as the normal Fourier transform. You have sines and cosines, but it's in 2D and it's wrapped around a sphere. And this wrapping it around a sphere makes things a little bit wonky and complicated, but it is in essence exactly the same thing. Right. So I'll show you the equivalent of the sines and cosines that we use for a spherical Fourier transform. And it is here somewhere. Yeah, straight from Wikipedia. And so what we see here on for each of these diagrams is like a world map. We have east-west along the x-axis and north-south along the vertical axis. Did I say vertical twice? Oh, so the first component here is the DC component. So it's just 1 everywhere. The next component, let's just look down the middle row first and ignore everything on the sides. As we move down, you see more and more oscillations from the north in the north-south direction. So this is the let's call it the polar frequency axis. So you can, it just goes on and on. And if we look at the little figures on the diagonal out on the edge, you see we get oscillations in the other direction, in the azimuthal direction, or the east-west direction, if you like. And between there, you have oscillations in both directions at the same time. Yeah, there's a little difference from the normal Fourier transform in that because things are wrapped up on a sphere, if you just made oscillations in the north-south direction and then in the east-west direction with equal distance, you would bunch up a lot of oscillations close to the poles. That wouldn't work very well physically or mathematically. So you see the vertical oscillations are sort of stretched when you get close to the pole. Yeah, but that's the only difference from a normal two-dimensional Fourier transform. And if you have ever read about ambisonics before, you have probably seen a different version of this figure. I'm going to show the second figure also, if I have it here. Yep. This is how it's usually plotted, where you have the only directional one here, which has no oscillation, zero frequency in both azimuthal and polar direction. And here you have a frequency of 1 in each of those directions. And you get these very nice looking figures as you go down, but they're not very, I don't know, it takes a while to get your head around them. It's easier to understand the previous figure, I think, and they contain the same information. Right, I think I'm going to play some sounds to make things a little bit more practical. So I'm going to take a recording that I did today, and I'm going to play this channel, that channel, and this channel. Okay. Let's see if it works. So then we need to go to here and play channel 1. Okay, if I press on, we want to view the video. This is 2026. Okay. Oh, and we also want to see the visualizer. There we go. What happens if I press play? Nothing. Is my audio setup okay? It seems to be. There we go. Okay, it's working. Let's see if it's. Okay, so microphone in the center, me outside, and as you can hear, it's pretty much the same sound all the way around, which as it should be, because we're now playing the ambisonic channel with frequency 0, 0, well, spatial frequency 0, 0. And in the energy visualizer here, you can see an analysis of the recorded ambisonic signal. Where you have the east-west, well, it looks like a globe. You understand how this works. I'll just play it once again. Okay. And I'll play another channel. Let's see how we can do this. Down, solo that, and play that. Okay. Same recording, just a different channel. Okay, so this was figure 8. It would be weaker in that direction and stronger on the sides. There's a limiter in here also, so I'm not sure if this is active. That would screw things up. Okay, and we can do the other figure of 8, which is at 90 degrees to this one. Okay, and the last thing I wanted to play was the very last channel, which has 10 lobes as you move around. Okay. And there are in total 36 of these channels, just like there were 36 beams. They are converted into 36 ambisonic components. And like I said, these can be converted back and forth from one to the other. And I also told you, given the 36 beams, you can create new beams in any direction that you like. It's actually easier to go from the ambisonic components to the beam in an arbitrary direction than it is to go from the porcupine to another porcupine. So that's one of the reasons why people prefer to use the ambisonic representation. It's a bit harder to understand, but it's easier to use once you've understood it. So do I have until 45 or until 7? Sorry, 45? No, proceed. Okay. Then I'll just quickly show you what ambisonic microphones can look like. So they have evolved a little bit over time. The first ones looked like this. Well, this is actually a relatively new one from Neumann or Sennheiser, but the design is from the 70s, and this looks like the first representation that I made with like these beams pointing out, except there are only 4 of them, and that's basically how it works. Also, each of these capsules have a little bit of directivity, and together they form an ensemble of 4 beams that you can manipulate in the way that I described. And this works because it's possible to physically create capsules that have the directivity that you need for a first order microphone. But if you want to go to higher orders and higher resolutions, this principle doesn't really scale that well. So what people do then is they make this kind of contraption, which is spherical, as you can see. Each microphone here, I don't know how many there are, but there are several hundred. They are omnidirectional. So they only get their directivity by being in an array with other microphones. So it does not work like a compound eye, where each eye looks in one direction. So every microphone looks in all directions. Well, more or less. I mean, if you're on the front side of a sphere, you hear more from the front than from the back, but there's not a huge difference. The main thing is the time difference between the different microphones. So you have it works like a phased array, which many of you might have heard about. It's used in radar, and it's also the way optics works, and yeah. Not going to get too much into the details. Yeah. So the third representation, I think I'll go a bit quick there, but okay. The third representation is the local field, because what I've talked about so far is things that happen in the far field. How sensitive is each channel to sound coming from a certain direction? That implies that the sound has been traveling, it's traveling in a straight line, and it's coming from far away in the far field. But when you make a microphone, you're very much more interested in what is happening very close to the microphone, because that's what you can sense. Let's see, do we have a... Yeah. So one of these beams that we looked at might look like this in the local environment around the microphone. You can see we have these straight lines right in the middle. So that's an imitation of a plane wave. A plane wave should have straight lines that go to infinity. Here it just straight within this little region here. And outside they look a little bit more spherical. So this is a very simple sound field. If we look at a more complicated sound field, we can look at a completely random sound field coming from all random directions. So it can look something like this. So you see there's like something happening here, but outside there it's just like a continuation which doesn't have any meaning. So the part of space that we have information about is a small area here. For a fifth order microphone, you have maybe 2.5 wavelengths across. And this is what you call the zone of reconstruction, or you could reconstruct precisely the sound field at the recording site. And because you can calculate this from the far field information that you have, this is why I'm saying that you can also emulate spaced microphone setups. Because if you want to emulate a microphone which is over here and another one which is here, it's okay, you have that information, as long as they're not farther apart than the size of the zone of reconstruction. Of course, the size of this zone is very frequency dependent, because if you have fifth order, you have 2.5 wavelengths, and a wavelength can be everything from 17 meters down to 17 millimeters. So this is a problem if you want to create a microphone, because the microphone has a fixed size. And that's something I've been working a lot on, but I don't think I'm going to take the time to explain what I've done with that. Okay, I have 10 more minutes. Okay, maybe I'll do a little bit more. Yeah, then I'll do the beamformer thing. I've been playing around with AI like everyone else, so I asked the AI to do me a little beamforming demo. Let's see where they have it. T7. Yeah, there we go. Some of you might have played around with something like this. Let's see. Yeah, can I get it down to size? Okay. Okay, so here we have an array. This is a line array, meaning that all of the microphones are on one line. It's one-dimensional, but doesn't matter. The basic problems of array beamformers is the same, whether you have 1 dimension or 2 dimensions, or whether it's flat or on a sphere. So we'll do the simplest case, which is a 1-dimensional array. Okay, so we have some microphones placed on a line, equally spaced. We can steer them from left to right. If you had a 2-dimensional array, we can steer them in the other direction as well. Okay, so let's say we want higher resolution. We try to add more elements. It doesn't really do anything. So the number of elements does not influence the resolution. What influences the resolution is the size of the array. So we can move the elements farther away from each other. There, now it gets sharper. Well, changing the size of the array does exactly the same thing as changing the size of the wavelength. What matters is the relative size of the dimensions of the array relative to the dimensions of the wavelength. So moving the slider up is the same as going down in frequency. Going up in frequency. Oops, if we go too high, this happens. This is not good. So this is something which can happen. You're trying to point a beam in this direction, but you get a beam in this direction as well. So this is what's called aliasing. It's a big problem, because once you have aliasing, you really don't know where the sound, you know very precisely that the sound is either coming from there or there, but that's not very useful information. So all of these microphone arrays, they have a limit, an aliasing limit, above which you don't get very useful special information. So that's one of the design limits we have to deal with. And to overcome that, what can we do? We can add more elements. That works, but it's very expensive, because let's say you want twice the density of microphones. That means you need 4 times as many of them, multiply by 4 a few times, and suddenly you have a very large number of microphones. And the precise limit where this happens is where the distance between neighboring microphones is half a wavelength. That's where bad things happen. Okay, but below there, you see the width of the beam is very much dependent on the frequency. This is also a problem, because the ambisonic standard specifies that every channel should have the same shape at all frequencies. And this is physically impossible to do. So what do we do? Some people have worked on this before me, and I have a diagram illustrating that situation. Here I drew that myself. So as the frequency goes up, the resolution goes up. The resolution here measured in ambisonic order, and it's pretty linear. This is a simplification. You can keep first order directivity across pretty much the whole spectrum, but as you go up in frequency, the resolution goes up pretty much linearly with frequency until you reach aliasing limit, and then the fun is over. So this is not good. If you want to have constant resolution over the whole frequency range, you want something else. And what people have come up with as a solution to this is this. So it starts to get a bit more complicated. So you have a sphere in the middle, which is the microphone array like the one I showed you before, and then you have a sphere outside, which is another microphone array, which is bigger. The idea here is you can use the outer microphone array at low frequencies to get high resolution, and then it will alias at a fairly low frequency, and then you switch to the inner microphone array. So then you have this situation. I drew that also. So you use the outer microphone array, you get the resolution quite quickly, then you alias, and you have to start using the innermost array, and then you get here. So the resulting curve is something which at least has a somewhat flat piece on the middle. Yeah, so all this is stuff which other people have done. Now I was planning to talk a little bit about what I have done, so I'll take a few minutes at the end to talk about that. So like you see, the microphone here, it is not spherical, it is very flat. The reason for that is there's no reason for it to be spherical. You can point a beam in any direction, even with a flat array. So here you have two arrays, one on each side of a baffle, and that makes it possible to point a beam in any direction. And the advantage of having it flat is that you can have as many radius as you want without making a contraption like this. So I'm going to show a picture from the inside of the microphone. Let's see. Yeah. So there's a bunch of microphones inside. There are 42 on each side, so a total of 84. They're more dense in the center, and then they get more sparse as you go out. So the idea here is that at low frequencies, you use the microphones around the edge. So you quickly get a high resolution, but they will also quickly alias, so then you stop using them, and then you use the next ring of microphones, and so on and so on. So there are 7 rings, so you will quickly get up to maximum resolution, and then you keep that maximum resolution across a wider frequency range until you alias. And because the microphones in the center are very close to each other, you can go to a very high frequency before you alias. It's the idea here. So let's see, I drew a diagram for that also. No, yeah, there we go. Okay, so that solves some of the problem. At least it improves the situation a little bit, because you can go quicker up, you can stay flat, and then you drop down at the end. But you still haven't quite solved the edges here, because at low frequencies, yeah, you would need to have 5th order. So I'm aiming for 5th order ambisonics here, and to get that at 20 hertz, let's say, you would need to have 2.5 wavelengths, and the wavelength is 17 meters. So you would need a microphone which was, I don't know, about 50 meters in diameter. That's, I haven't done market analysis, but I don't think I would sell a lot of those. So the only thing which remains to do then is to cheat. So we have to use signal processing to sharpen up the signals. And I'm just going to give you a hint of how that works. So the reason why we can do some cheating here is because of the way we hear. It's very different from the way we see. In the physics, it's also not so different. We have its wave propagation in both cases, but when we look out at things, we are mostly interested in the reflections of the light sources. So we try to avoid looking directly at the sun. Our lamps have lampshades. We don't want to look at the light sources. We look at the reflections, and they form like a continuous two-dimensional field of hues and colors. When we listen to sound, we don't have that option because we only have 2 sensors. So what our ears and our brains are trying to do is to extract information about sound sources to the extent possible. I mean, we're also interested in reflections. They inform us about the size of the room and the distance to sound sources, but our primary interest is in the sound sources themselves. So I'll illustrate the situation like this. Let's say these are sound sources. We have 6 sound sources. Okay, so those are the ones we are interested in, but we have a very low resolution array. So what do? If we assume that these blobs are created by point sources, then it's possible to estimate the precise center of each blob, like so. Oh, I was a bit unclear, but well, you get the point. And given that, we can synthesize a new signal where the sound coming from each of those blobs is made perfectly sharp and placed at the center of each blob. This doesn't look like it would work very well, but it sounds very well. I mean, it fools our auditory system because any errors that we make in this process will be smaller than the errors that the human being makes, which only has 2 channels. So we can fly under the radar of psychoacoustics this way. And that is how we arrive at a resolution which is flat like this. We take the parts which doesn't reach 5th order, we upsample it to 5th order with nonlinear magic, and then we cut it off where the physics goes beyond 5th order, and the result is a flat 5th order signal. Okay, and that was what I was planning to tell you tonight, and we have a little bit of time for questions.